What's up everybody? Hope you're doing good today. Another video programming for data analytics 2. Today we're looking at a very cool subject. We're going to try to use scikit-learn's linear regression to try to predict the Ethereum closing price of the day using the Bitcoin cryptocurrency's opening and closing price. So we're going to build a machine learning model that can try to predict what the closing price of a different crypto is going to be based on Bitcoin. Now there's a reason why I'm doing this. If you know a little bit about crypto, you know that Bitcoin was kind of like the big ruler for a long time, and it was the primary one where you could buy and sell from like normal currencies, fiat. And so it's in a way, for a long time, there's been that tether that whenever Bitcoin goes up, Ethereum goes up, and when Bitcoin goes down, Ethereum goes down. And it's not just Ethereum, but it's pretty much most of the in fact, all of the altcoins outside of something like USD Tether. But of course, we don't know this. We want to, and we don't know to what extent that is. So we want to see if our model can kind of discover that trend, even if we didn't know it, and just to see how close they really are. Okay, so let's go ahead and I'm going to do this from scratch, although I am using scikit-learn's linear regression, which is the point of this. And I think this is a data set that I found online and I applied it. So this is my example that I came up with. But I really, when I go on in the next videos and I talk about other machine learning models like SBMs or neural networks or deep learning, I want to see if I can actually use the same model and compare my results to this and see how close we can get, like how good can we get of a model. So I really spend the time kind of preparing this so that we can use it in the future with other models. So I'm actually looking forward to that. But today, we're just going to do a simple linear regression. So this is kind of like the summary of what we're going to do. First of all, we're going to get our data set, and I'm going to show you where I got that from so that you can download it too and play around with it yourself. And then once we go ahead and get that data set, we're going to have a little bit of pre-processing, so a little bit of cleanup. And primarily that is going to be to make sure the data set is nice and complete, because we are going to be looking at historical prices from Bitcoin and Ethereum. We want to make sure we're looking at the same time periods, and Bitcoin's been around longer than Ethereum. So we're going to do a little bit of pre-processing there. Once we go ahead and do that, then we are going to go ahead and generate our training and testing data sets. So we're going to do a split. I think I'm going to do 20-80. So we're going to do 80% to train, 20% to test. We're not going to do any validation right now, just 80-20. Once we do that splitting, then it's time to go ahead and feed it into our model. So now we're going to go ahead and fit, or in other words, run the linear regression. And this is the part where later on I'm going to, in the future video, I'm going to try to use a different model here, because everything else here is going to pretty much be all ready to go after this video, so that you can try out other models and or even modify it to try other coins. Since the data set we're going to look at does have more than just Bitcoin and Ethereum. In fact, thinking it might be fun if you guys try with Dogecoin or something. So we're going to go ahead and do that training, and then we're going to test it. So we're going to test our model using the predict function, and we're going to basically test it to see how good the model works. And of course, we want it to work really well. If you've seen the previous video, then you saw me talk about accuracy and how measuring something in terms of accuracy when it comes to regression does not give you the full picture, because even if your model does not nail any single individual point, does not get the exact answer, that doesn't make it bad, because if it's off by a couple of pennies per se on the model that's dealing with money, that's actually really good. As long as you're off only by a couple of pennies plus or minus every single time, even if you never get the exact number, as long as you're there, that's really, really good. And it's much better than a model that is off by hundreds of dollars every single time. So there has to be a different way of measuring it than just like whether something is correct or wrong. And so the different metrics that we have are things like root mean square error and mean absolute error. And we said that root mean square error is good because it is sensitive to outliers, whereas mean absolute error doesn't have that issue with outliers. So if you don't care about outliers that much and you want to give it an equal amount of error per test point, then that's a better one to use, right? But they both have their merit. And then of course there's things like R2 score, which we want it to be close to 1, but we know that we don't want it to be exactly 1, because things can be kind of suspicious at that point unless we're really, really good at our models. And so those are the kind of things we're going to do. So we're going to predict it, and then we're going to go ahead and evaluate it by looking at the metrics. And then maybe, you know, maybe it doesn't look as good, but we will try to do some graphs so we can visualize it. After all, we want to be able to present this to our boss so that he can invest in crypto or whatever. Or in the right crypto, I suppose. Okay? So that's kind of the plan for the game plan for today. And I played around with it before, so I think we should be, everything should work out. So we'll see. All right, so the first thing I want to show you is, like I said, the data set. And so the data set I found on Kaggle, and it's not originally from Kaggle, but I will leave the link in the description below. But I just Googled like crypto historical prices data set, and this was the second one that I found. The first one I found was like 4 years old or something, and it was not updated. Whereas this one appears to be constantly updated. Constantly, because I mean, the last day of the data set that was updated was like August of 2021, and this video is being recorded in February of 2022. So, well, it's a little bit outdated, but it's not, at least it's a couple of months versus a couple of years. However, this data set is not something that these people came up with, or this person. They actually got it from investing.com. So you could probably go there, and they do have a link that you can check out. I didn't go there, but you can go there and check out the original data set, where this is coming from, and probably be able to get out more up-to-date data if you actually wanted to run this with like today's data per se. So, you know, basically the data set is a zip file that contains a bunch of CSV files, and we know the CSV files are comma separated value files, so they're like little spreadsheets per se, like mini Excels, and they are split by coin. So we got Bitcoin, which is the one we're going to be looking at. We also have Ethereum. There's Ethereum Classic, which is different than Ethereum. Don't get them confused. And then there's Dogecoin and Cardano and a bunch of the coins that you would know and love, right? So so you go ahead and you download this. It's gonna make you register with an account. You gotta put a valid email because they do send a confirmation email. So just put in something and then download it. Okay. And once you download it, what you're going to be looking at is going to be a file, and in that file you're going to find the CSV. So I went ahead and I extracted. I extracted Dogecoin, but we're not going to use it. So I extracted Ethereum, and then I also have Bitcoin in here, in the same directory where my Python file is going to be at. Okay, if we go ahead and we take a look at what that looks like, I went ahead and used Linux here. So it's head Bitcoin, so we can see what it looks like. This is also in the documentation here. So you can see here the contents. It says dataset has 50 different CSV files for the top 50 cryptocurrencies. Price history is available on a daily basis from the launch of the respective cryptocurrencies. That's important. So the dates are not going to match because, again, Bitcoin launched before Ethereum, so there's going to be more rows for the Bitcoin file than the Ethereum file. Okay, and the columns are going to be serial number, date, price. Now, in this case, price, what it really means is the closing price. So this is what we're looking for. We're trying to predict what this closing price is going to be. And then we have the opening price. And then we have the high and the low volume change. We're not using these today, but like I said, I do want to play with this data set in the future with other scikit-learn models, and maybe we'll use it there. So I did basically, we are going to be downloading, pre-processing this and having it ready to go. So in the future, we can do that, or you can try experimenting and playing with other of the columns. And by the way, if you haven't guessed it, these are going to be our features, basically, that we're feeding it. But we're only going to be feeding it right now 3 features, which is the opening and closing price, so the open and the price column by names of Bitcoin, and then the opening price of Ethereum, and then the Y, the one we're trying to predict, is the closing price of Ethereum, which is here is under the price column. That's the one we want to know, because again, we want to know if based on the opening price and based on how Bitcoin performed that day, what the closing price of Ethereum is. Now, of course, if we know the closing price of Bitcoin, then I guess by then, technically Ethereum's closing price is already out there, right? So I mean, our model isn't really gonna do much because we could just, if we already know the closing price of Bitcoin, then we already know, but it's still a good exercise to do. Okay, so you can see here, if I go ahead and look at the CSV file, it is indeed set up. We have serial numbers which start counting, they're like row numbers. We have the date, and that's the day of the coin price. And then well, the first couple of the Bitcoin ones, there's not really any useful information. But here, let's look at the Ethereum one. So the Ethereum one, we can see the date of 2016, March 10th. the price was 11.75, and that is the price, so that means the closing price. And then the opening price was 11.2. So we started out at 11.20 cents and it closed at 11.75. So we can say it went up that day. Okay, and then we got all the other stuff in there. And then the next day, it opened technically at that price, that 11.75, and then it closed at 11.95. Now, the reason why these numbers are like that is because technically it's not like the stock market where there's an opening and closing time. With crypto, it's 24/7, yay. So I believe that what they consider close is just going to be like midnight sometime. So yeah, close enough. Okay, pun intended, I guess. So this is what the files look like, all right? So now what I said we want to do is we want to load in our data set into Python so that we can start using it. And so there's a lot of ways that we could open up the CSV file in Python. However, because of how scikit-learn works, best thing to do is to load it as a pandas data frame. And so that actually is a good thing because there's a function that will do all the hard work for you. All you're going to have to do is one line of code, and you're going to be able to open this CSV file as a data frame in Python. And a data frame in Python is going to be, a pandas data frame is basically going to be a nicely formatted table where everything is mapped correctly. And we'll explore it in a minute. So let's go ahead and do that. So again, we are going to load the CSV into a data frame. And how I'm going to do that is first I need to use pandas for that. So I'm going to import pandas as PD. So that's my import. So I use that library in. So there's a pandas, it's a library in Python that we can load. If we want to use it, we want to tell the operating system like, hey, load the files, we're going to be using them. So that's what that line is doing. And then we're going to make a variable, which I'm going to conveniently call Bitcoin data frame. So BTCDF, but this is just the name I picked. And what we're going to do is we're going to use a function called readCSV. And this function, as you can see the documentation, but what it takes is first it needs to know the file name. So in this case, it's bitcoin.csv. And then from here, you want to pass the parameter for the sep, which means separator, which what it's doing is it's saying, how is this file like? Because even though it's called .csv, Python or pandas doesn't know that. So you got to tell it like what kind of way is the data split. And it turns out that data is split with commas because it's a comma separated file. So that's why we put a comma under the sep argument. And finally, the other one I would recommend that you pass in is the header. This is technically by default infer, but we're going to explicitly say that just to avoid any confusions. What this is doing is, but when it says infer, this is like pandas do your magic. Basically, it's going to look at the file. It's going to see that the first column of the file contains actually the column names, as you can see here. Sorry, first row of the file contains the column names. And so it's actually going to be smart enough to figure that out, that this is like, oh, these are actually the columns and this is the data. And then it's going to then name our columns based on what the first row names are. So it'll know that this is called the SNO, the numbers. It'll know that this is called the date and that the price is called this column of file. So that's what's happening. But you could manually pass a different number here if you wanted to say that the column names are in a different row, or if there aren't any column names, we just put a 0 or something. Okay? So once we do that, to confirm that this worked, let's go ahead and print out the contents. So I'm going to say print btcdf, which is the name of the function, and I'm going to do values. I'll show you the difference between just printing it out with and without the word values in there. So let's go ahead and run it and see what happens. So as we can see, this is indeed loading the data, and we can see that it is in a list in Python, and we can see that the numbers actually match what is up here. So we got 1, 20, 10, 0, 7, 18, 0.1. These dots means that there's more columns that is not being shown here, all the way to the end, and then the bottom line. So how can we see that's correct for the bottom line? We can use a tail command and put the file name, and we can see that, yep, it is indeed correct. We got all the numbers up to the last day, which was just updated, which was August 24 of 2021. Like I said, about 6 months ago. Very cool. So you can see that it read it successfully. Now here, let me just show you what it looks like without the word values. you'll see you get almost the same thing, but here you get the column names up here, so you can see that. But it doesn't really line up that pretty. Well, actually, no, actually it does kind of line up pretty, because this is actually the index that pandas is giving it versus this SNO, which is like an actual column name. This will prove to be an issue we'll have to fix later. But yeah, so that's just the difference between that and values. So you can use either or, big deal. But yeah, okay. So let's go ahead and do the exact same thing and read in the Ethereum one. So I'm just going to go ahead and make another variable called ethdf, and I'm going to call the pd read function, read CSV, ethereum.csv, same separator. In fact, I'm probably should just copy and paste the line above and make it easier. Or better yet, I could make this, if I was reading a bunch of files, I could make this into a tiny function and just pass as a parameter the name of the file. That would work too. Let's comment this out so we don't get like a billion different things printing out. And then let's go ahead and just confirm. I like to confirm that things are working as I do them to avoid having to go back and fix broken stuff. So we can see that the Ethereum one looks about right, but let's confirm it with what we had here. 1175 for the top. Yep, that's right. And then for the bottom, yep, 194. Okay. So we got our data read in successfully. If you want to find out more information about this read function, I will go ahead and leave the link to a documentation from Pandas. So this is Pandas' official website, and in here you can read about this read from CSV file. So I'll leave a link in the description below to this one because it's a great function and it can do a lot more than what I'm showing right now. So just wanted to point that out. Okay, so like I said, right now, if you see, if in fact here, let's just print them out both out again for a second. You can see that the Bitcoin one starts in 2010 and the Ethereum one starts in 2016. They both end the same day, so they will end the 24th of August of 2021, but the beginnings are different. And because I want to do the training and have basically, you know, the inputs and the outputs all be lined up, I have to make a decision here. Like, what am I going to do with the dates that I don't have for Ethereum that I do have for Bitcoin? And so for the sake of simplicity here, we're just going to chop it off. So I'm gonna just get maybe like everything from 2017 and on. So we're gonna chop off basically about a year's worth of dates for Ethereum, and then like 7 years worth of dates for Bitcoin. So I just have a nice chunk of there's gonna be almost 4 years of data, but they all line up nicely, okay? So how do I do that? Well, this is good because you get to review how to manipulate these data frames to remove rows, columns, and all these things. So that's another reason why I'm doing it. Okay? So again, what I want to do now is my cleanup stage or pre-processing stage. And so the goal here, and I like to write comments because they remind me of what I'm doing, and also in the future when I look at my code, I can see what I was trying to do. And by future, I mean next morning after I woke up and I forgot what I wrote. But yeah, so I'm just going to go ahead and get basically 2017 to 2021 for both, okay? But to do that, I need to find where 2017 starts by finding out that row number, okay? So one way I could do it is I could just open up this file in like Excel and start scrolling down, but we're computer scientists. We don't do that stuff. We automate. Even if it takes longer to code the automation than it would to just look at the file, we're still going to automate it because darn it if we're not, okay? So get motivated and start automating. All right, so I'm going to do a little for loop. And how am I going to do this? I'm just going to go ahead and iterate through every single row in the Bitcoin file because it's the one that I want to chop. Well, I'm going to have to chop them both, but let's start chopping the Bitcoin one. And I'm just going to write an if statement that is checking whether the cell that contains the date number is going to be containing the number 2017, because these go in order. The first time I see 2017 is going to be probably the first of the year, right? So here's another interesting point, and this is why the data frames are awesome. Notice how I'm accessing the column of date. All I gotta do is type the name of the data frame, which I assigned up here, and then I'm putting in under the array, the square brackets, the array index access operators per se. I'm just putting the name of the column, which as a string, which is called date. And then this kind of, if you remember hashing, this is basically how that's kind of working. It's kind of like a little hash, and it just knows that this is the column you're referring to. So that's just awesome. Very, very nice and readable code if you think about it. It says here for row in the date column. All right, and then my if statement, if 2017 is found in that row value, that's when I know that I found it. So let's go ahead and just print out the row content and then print out my count. And if I don't find it, and then of course stop at that point iterating, otherwise I'm going to be printing all day here because there's tons of numbers after 2017, and I want to print out the first instance of it. So once I go ahead and figure that out, I want to stop that loop. If the number is not found, I want to increase my count so that it counts up to that. So let's go ahead and run it. And I should have commented this out. Now we're going to clutter our terminal with all this stuff, but it's okay for now. But if you look at the bottom, we can see that the first time we see it is 2017-0101, 2359. So that must be row number 2359. Okay, so we can write it here as reference that it is 2359. So there we go. Successful automating completed. Okay, so we just have to do the same thing for Ethereum. But again, let's finish with Bitcoin first. Okay, so we know that any number after that, any row after that is going to be after this day, which is what we want to keep. So the next thing I'm going to show you is how to remove rows or columns from a data frame. Okay, so for that there is the drop function. So I'm going to leave a comment with this one's not from pandas, but it's just from a website that I found, but it's still really, really nice, and it talks a lot about how to use this drop and like all the different features and functionalities. They're like, again, it's like a Swiss handkerchief, you know, the little Swiss blades that have like 10,000 things in one. That's literally what the drop is. But as a brief overview, you can see that it's actually pretty descriptive. The function is called drop, and you basically tell it whether you want to drop a column or a row. And that's what your axis is. So if axis is 1, it's going to be dropping columns. If it's axis 0, it's going to be dropping rows. And we're going to do both. Right now, we're just going to drop the rows we don't want, but later on, I'm going to drop one of the columns just to show you an example of that. And also because we don't need that serial number column. It's just kind of useless because we have our own indexing. So yeah, in place means whether you want to when you do the deletion of the rows or columns, do you want to delete the original version that you're calling it from, or do you want to make a copy with the deleted stuff? So if in place is set to true, then it's going to modify the only version of this that you have. If it's false, then it's going to make a new copy with the removed stuff, but not touch the original. If you want to preserve integrity in that sense. Labels. In the scenario where you're deleting columns, you're going to pass in the column names there. In the scenario where you're deleting rows, you're going to pass either the numbers of the rows you want to print to remove, which if you have like 1 or 2, you can just pass that index. But if you're actually removing like a bunch of them like we are, you actually want to pass a range of them. Okay? So I'll leave that in, if you want to read more about it, I'll leave that on the description below as well. Okay? So in our case, we want to go ahead and remove all the rows from basically the beginning up to row 2359. So I'm going to go ahead and create a brand new copy. So I'm not going to do it in place. I'm going to make a new one because I like to keep the original there in case I ever need to refer to it. Like if I ever want to go back and try something on 2016 data or something. Okay. So I'm going to create a new variable. It's going to call clean BTCDF, so clean Bitcoin data frame, their original variable name. And I'm going to call it on the original one, so Bitcoin DF dot, and then the drop function. And then you don't have to do it in multiple lines, but I'll stick doing it that way for the first example, so it matches the documentation that I showed you. But then for the Ethereum, we'll do it in one line. So in this case, I am going to be removing the number of rows that I care about. So I'm going to use a range function for that because it's going to return basically all the rows as numbers. So it's like 0, 1, 2, 3, 4, 5. And in my case, I want to remove from 0 all the way to 2359, not including 2359, because that's actually one of 2017. But remember, sorry, that hurts. The range function does not include the ending one. You can see here that it says returns an object, blah, 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 blah. Starts defaults to 0 and stop is omitted. Okay? So does not actually exclusive of that step. So it does not include that. So that's why I put it here, because it will not include the number there. It'll basically end at row 2358. Now you don't have to hard code it like I did here. In fact, I would discourage you from doing that. You can just go ahead and just pass the count variable too, and that would be just fine too. Either way, you know, I suppose doing it this way makes it more robust. So if you feed it future data that is not matching exactly because they added some stuff, your code doesn't break. So I think count is good here, but just know that what is being printed there is essentially this number. Okay, at least as of today. Okay. So that is going to be my range. Like, oh, wait, comma should go here. Like I said, we're removing rows so that we put axis 0. Again, if we put 1, that's for columns. And because we are going to be making a copy of this that is with the remove rows, but not touching the original, then we want to say false for the in place. Once you do that, then it will be good to go. It'll remove them. So if we would like to see that, just to very quickly see if that worked, we can do that. We can just go ahead and print out clean btcdf. And I'm going to print out also the original one so that you can see that it hasn't been modified. And also, did I comment the other ones out? Yeah. Okay. We don't need to print that, but I'll leave it there for now. Okay. So you can see this is the original one. You can see it starts at 2010, and then the clean one starts at 2017. So great success. All right. So we haven't modified the original, but we made a new version that is nicely cleaned up. But you can see the serial number thing now starts at this number instead of starting at 0. That's why I'm going to get rid of that column later, because it's kind of pointless to have there now. So yeah. Okay. So like I said, let's get rid of that. Let's just get rid of that so I can show you an example of removing a column. So let's get rid of this SNO. That's just useless numbers now, since we have our own indexing system. So for that, I am going to just go ahead and do an in-place one. Now we're going to have to make an entire new list just to remove the row. Okay, so let's go ahead and drop first row, which is called SNO, like that. So I'm going to say clean btcdf drop, and then again this time I'm just doing it in one line. So I'm going to say labels. In this case, the label is not a range of numbers, it's just the name of the row that I want to remove. So it's going to be SNO. You put it in square brackets because you're giving it a list of rows that you want to remove potentially. In this case, it's just one, but still a list. Axis in this case is going to be 1 because it's a column that we're removing. I said list of row, well, you know what I meant. And then it's going to be in place, because this time we are going to basically just delete it from the existing modified list. I have an original one called btcdf, so from now on I can just modify the same one over and over again because I have my quote-unquote backup. Okay, so if I do that, then you know, run it again, and this should have removed it. Ooh, SNO. Oh, it's uppercase N, right? So you have to make sure that this is case sensitive. You gotta match the column there exactly. Okay, we can see that now that SNO column is gone. As you can see, it's no longer there, and we're good. However, notice that these numbers are not starting from 0 for the indexing here. This is a pandas column, so this was not in our existing data. I know that in our data we had this sort of row column thing here, SNO, but this is a new thing here. I don't like this because this will cause some issues later when we try to line up both data sets. So I want to reset that row count, particularly because it's like, I mean, it's not too bad because I mean right now it's just starting from this number and on, but like if we were removing pieces of rows all over the data set, this number would not be lined up and nice. So resetting indexes is a good thing, and I'm going to go ahead and do that to make this look prettier. So I want to reset the index, since the row removal doesn't do that. To reset the index is a pretty nice and simple function. it's called reset index. So you just basically pass in the data frame that you're working with, and then call reset index, and then set drop to true so that it actually drops the stuff you don't want, basically. Okay. If we do that, then you will see that now it starts at 0 and everything is nice and happy. Do I have anything about that? I do have, yeah. So I'll leave a description below on this function of reset index. It's from the pandas documentation, and it talks about how this indexing works that I'm talking about and how you can use this reset for it. Also talks about some really cool slicing things you can do for it. So again, I'll leave the description below. This one's official pandas documentation, which it's amazing. Like, you know, there's a lot of stigma about documentation because back in the day, they were like books, and like nobody wanted to read a book like for documentation because they're lazy and they were like, But now it's all websites, and they're actually pretty good. Like, people understood that like we don't want to read like a massive amount of data. We want to see examples, and we want to see short data that we can reference quickly. I think people figured that out. So now documentation is much better than it used to be. So it's actually enjoyable to read the documentation of things. So I encourage you to check it out. Okay, so switching back to this. We pretty much have it all set now for this. We have the data where we want it to be. Now we got to do the exact same thing for Ethereum. So let's go ahead and do that. So I'm probably just going to copy and paste it and just tweak it. So basically, do the same thing for Ethereum. What I want to do first, again, is remove the rows I don't want because I want to start from 2017. So I'm just going to, again, I should have made this a function. Technically, if you're going to do this more than twice, I would do a function for sure. Except in this case, I'm not going to look at the Bitcoin list. I'm going to look at the Ethereum one. But everything else is going to be the same. Let's print it out. I'm actually curious. Let's just run it, see what that number is now. 297. So we're only going to remove 297 rows here versus where we were removing over 2,000 for Bitcoin. Okay? So, cool. Let's go ahead and copy over the dropping of that rows. So this one we're going to call clean Ethereum. And make sure when you're copying and pasting, you don't screw this up with the variable names because bad things can happen. And so, yep, all this drop, this count, in this case, it's going to be 297, which is going to take the count from here. Everything else should be the same. And then we can go ahead and drop that first row as well so that both our tables have the same number of rows. So switch this to ETH. Then we want to reset the indices too. And then let's print it out and see if everything worked out. Hold on, remove this row C there. Okay, so we can see that, yeah, it went ahead and removed the SNO column. It reset the index of the row. So we basically did the same thing. Also, an important point to note is that now the Bitcoin one has 1,697 rows, and so does the Ethereum one. That's what we want. We want them both to have the same number of rows because now I'm going to union them together and basically, or join them together based upon the date or the row number. Either one is fine. And then make one big data frame. That's going to be the next step, basically. So I'm going to put it all together into one data frame, and that's the one that's going to be nice and ready to go for any future projects we want to do with it. Okay? So even though we saw it, here, let's comment some things out now. So let's print. So again, I don't like cluttering. Let's just take one more line of code here just to check whether the lengths are truly the same. So check that, compare the length of that with the length of the clean Ethereum one. We can see the word true is there. So it worked indeed. They are indeed equal. So very good. Everything is going as foreseen. As you see, the life of data analysis person, most of your work is going to be on cleaning data. But that's okay. That's part of the fun. Okay, so let's actually do the machine learning now. So now that we have our data, well, based on our to-do list, let's gonna go check it out. So we got a data set, we did the pre-processing. Now we're gonna wanna do the train and test split of the data so that we can train our model and then be able to test whether it worked or not, okay? So let's kind of summarize what we wanna do, okay? So as input, we wanna take the Bitcoin's open and closing price. And then we also wanna take the Ethereum opening price, okay? Then as output, we want the Ethereum closing price. The idea is to see if we can predict the closing price. Oops, hold on. The closing price of Ethereum for the day based on how Bitcoin performed the same day. By the way, it would be cool later on to try to do this using the day before, because that actually would be actionable data that we could use if we were connected to a brokerage or something. By the way, this whole video is not financial advice, okay? Just want to put that out there so I don't get sued. Okay, so we want to we want as input BTC opening and closing price. We also want the Ethereum opening price. As output, we want the Ethereum closing price. The idea is to see if we can predict the closing Ethereum price for the day based on how Bitcoin performed the same day and what the starting price of Ethereum was that day. This is to see if there is a correlation between both cryptos, which, if everything is to believe, that should be the case. But we are going to prove it ourselves. We're going to follow the science. Okay? So, all right. So the first step that we're going to do again is we want to make our final like data set. So we're going to just kind of Lego. Let's Lego both data frames together. Lego is not a technical keyword for this. Came up with that like 5 seconds ago. Actually, no, actually is that for a long time, but I don't think anyone else does. But yeah, we want to glue them together, okay? So I'm going to make a new variable, so new data frame. I'm going to call it BTC ETH data frame. And I'm going to be using a function known as the concat. So for that, I have my last reference of the day, which is from the pandas documentation that is known as the merge, join, concatenate, and compare. This one's deep, it goes hardcore. Like you gotta know some SQL, like relational database knowledge to understand some of these terminologies. So I'll let you play around with that. But what we're interested in doing is we want to take both tables and basically put them side by side. So we want to do what is listed here as concatenation. So I believe it is, I think it's this one's the one that we're using. Yes, probably this one or the outer one. Yeah, I think this one's the one that we're going to be using. So you can see we have column tables. So we have 2 tables, and then they just kind of glue them together here. However, in this one, because it's using the indices, you can see that this table is missing like index, for example, 1. So this is empty for those. But of course, in ours, that won't happen because we have all the indices matching because we reset the indices. And that's kind of why I did that, because I knew this would be an issue. So yeah, so you're more than welcome to look at this. If not, you're more than welcome to just do what I did in my specific case. But, you know, just know that you don't have to do some crazy coding to be able to combine tables. You just got to pick one from there. Just literally look at the pictures. Even if you don't understand relational databases or anything like that, just like look at the pictures and see which one you want to do. Like you want them to glue them like this. You want to glue them like on top of each other, like one after the other. You want to do some special glue. There's a lot of ones over there. So like you'll find the one you need. And if not, then just keep trying them out and see if that's what you want. If it's not, then try another one and you'll eventually work it out. If you have trouble gluing things together or Legoing them, leave a comment in the description, below, and let me know, and maybe I can help out. Okay? So we're going to use, like I said, concat. So that's going to be the function that we want to use. And this function requires you to pass the 2 data frames that we're going to be Legoing together. So that's going to be the clean Bitcoin 1 and the clean Ethereum one. And then you gotta tell it an axis. So in this case, we're gonna do the leg one using the one, so the column wise, and then outer join. Again, this is this is the only part that might take a little bit of expertise to understand what the function you should be calling is and what the parameters are. But if you actually spend time reading that, you'll understand it. It just takes a while. That's the one big documentation. But like I said, it's actually useful. Very useful stuff. Okay? Or take a SQL class and you'll pretty much learn about joins and union and all that stuff there. Anyways, like I said, the best way to know if this worked or not is just to print it out and see if it's like what you expect. So let's print it out and make sure that I'm not messed up myself. Okay. So yeah, it looks like it worked. It's kind of hard to see because it's cutting some columns off here. But we do have an issue that we're going to have to deal with right now. If I were to print out the column names, so let's print out the column names, you're going to see that we're going to have a bit of an issue. And this is actually another way to test it if it worked by looking at the column names. So BTC EDF dot columns, that'll print out the list of columns, literally the list of columns. That's actually the right terminology for that. You got 14 columns now because each one had 7 before. And you can see it has date, price, open, high, low, volume, change percentage. And then again, date, price, open, high, low, volume. So it's like, Houston, we have a problem. We have basically 2 columns with the same name. And you can see how that's an issue because if I try to say something like print BTC ETHZF price, and then print out like the first item of that, or just random item. Okay. We have well actually I don't want to blame that just yet. Did I screw up the name of that column? Price. Nope. So I think that's an example of the issue that we have, that it doesn't know which column I'm talking about. It's like, yo, there's ambiguity here with the column names, and it's not quite good. But I want to make sure that's not just me. Did I? What happens if I do that? Still gonna send here? No, doesn't give me error. So I think that one's just tripping. That one is got 9. Okay, there we go. So it wasn't tripping actually. It is able to do this, but it still has the same issue. So I am saying, okay, print out the price column. Give me the values of that. So just give me the instead of giving me a data frame back or like a fancy object back, give me a list by. So I say call values, and then just give me of that list of the entire like massive amount of rows. Just give me a row basically 10 because it goes from 0 to 9. Or starting at 0 is the 10th row would be 9, and it gives me back the basically what is a really weird representation of that, which is 904. Oh wait, no, like I guess that's actually the 9th row. Technically, is it here? Let's pick like 2 here so that we can see it. 1033. So you can see up here it says 1033.3. So you can see that matches. We can't see the second price one because it's all the way to the end. But what I'm trying to get to is that this is an issue because this is actually Bitcoin's price and this is Ethereum's price, but they're both called price. So I don't like that because that's going to be a pain to work with later on. So we need to rename the columns so that they all have unique names and they're not confusing at all. So let's go ahead and do that. Let's go ahead and rename the columns. So let's rename the columns and remove the duplicates. Okay, and which duplicates do we want to remove? Only the date, because everything else is unique. Like even though we have two columns named price, one of them is actually Bitcoin and one is Ethereum. But technically we do have two columns called in fact here, let's Control Z all the way back to this. If we go ahead and call out the date one here, you can see that both dates are the same because we did the union. In fact, that's a good thing that they're the same. In fact, I would say this is a good way of verifying that. So we do actually want to remove one of the date columns. So we want to remove one of the date columns, and then we want to rename everything else. So let's start out by renaming the columns, okay? So we're still kind of doing a little bit of cleanup stage. And then remove the duplicate date column, okay? So I'm gonna go ahead and say BTC ethdf.columns, which we know would normally print the columns, but in this case I'm going to assign it. And what I'm going to assign to this is going to be the new column names. So to make my life easy, I'm going to just copy and paste this. Like this, and then let me just spread it out so it's easier to see. So I'm going to call them the Bitcoin ones. I'm just going to add the word BTC in front of it. Like this, oh, all the way there, and then like that. And then for the Ethereum ones, I'm just going to add the word ETH. And I know that the date one's duplicate. I'm going to get rid of it in a minute too. Let's move that one up here so I have space for this. Okay. So there we go. If we then call the print function again, let's see if it worked. Yep, all the columns were renamed successfully. So let's go ahead and just drop that useless column of Ethereum date. So I'm going to say BTC Ethereum DF dot drop. And then I'm going to pass in the label that I want. So it's a list again. You pass a list of labels, which again is just going to be one value in this case because we're only deleting one label, one column, which is ETH price. And, oh sorry, ETH date, not ETH price. And because it's a column removal that is access 1, that's really annoying, the documentation popping up. Like, I love the documentation, it's great, but like, it's actually starting to become annoying. Jesus, go away, please. Any place, true, because I don't want to make a new list out of this. Like I said, I have my original one, so from now on, I'm just replacing what I have. It's easy that way. Okay, so if I do that, then let's actually print out the columns again. Let's see if that one's gone. So yeah, we do have it gone now. And the date one's just conveniently called date, which works out actually. I forgot to put BTC in front of it, but I'm going to keep it that way because it's better that way. Date just works. So yeah. Okay, so now we're really done with the cleaning and we have one data frame with what we want, like all the features that we want on the output, input, everything is good to go. Now we want to make our training and testing data sets, right? So what we need to do is we need to create a couple of variables that are going to be lists of the X and the Y's, okay? So let us start by making our features. All right, and remember that the closing price is called price. So like this is technically the closing price, what we're looking for. When you see the word BTC price and also ETH price, just so we don't get that confused, all right? So I'm gonna make my X value, I'm gonna call it X, crypto X. And then I'm going to take BTC's ETH DF data frame. And I'm just going to take a couple of the rows from the columns from that, which is going to be the Bitcoin open, the Bitcoin price, and the Ethereum open. And I'm going to copy them over. So copy function copies over data frames content that you're selecting. So in this case, what I'm saying is I am taking the data frame that I cleaned up and everything is nice and tidy data frame and everything. In fact, copy that out so we don't see it. Actually, you know, let's print it out right here. Like, you can see what it looks like, and then we don't need that. Let's see, print that out. If you run it, you can see what it looks like now. We got date, Bitcoins, Ethereum stuff, all the way to Ethereum change. So I'm going to take this, 13 rows, 1,697 columns, and I'm going to take that, and I'm only going to get the following 3 rows. The opening price of Bitcoin, the closing price of Bitcoin, which is called BTC price, and the opening price of Ethereum. Those are my X values. So that's my inputs, my features, 3 features. I'm going to copy those into a new variable called crypto X. And now we're going to make our Y, which are just our outputs or our predictions that we want to match against the correct ones, the ground truth per se. I'm going to call that crypto Y. And that one's going to come from the one column that we know is what we want to get, the answer. That one's called the Ethereum price. Okay? So that was the closing price. That's what we want to predict. But we need to know what the right answer is so we can compare it with our model's prediction and see if it's good or bad. So that's the Y's. So yeah, that's our X's and Y's. So now we just got to split it 20-80%. Now there's a lot of ways that you can split it. You could just use slicing and just get like the first 20, the last 20, the middle 20, cross-validation, etc. However, this is a time series at the end of the day. And so if I just cut 20% from a specific spot, I argue that's not a good representation of whether your model is good or bad, because your model should work for all time because you're training it on all time. And by all time, I mean 2017 to 2021. So if I really want to show whether my model is good or bad, I should be able to test it within any point from any time, any point in that time period. And it's also going to be better working that way because it has training from the entire time range versus like missing the last year of the data, essentially, which would be like the last 20% or something. And so I want to, at random, get 20% of the time series so that it's a fair distribution of that. You know, we don't have trends affecting it. That way, like an example is like, suppose that crypto for the last, from 2017 all the way to like middle of, or to the beginning of 2021 was like always up. And then all of a sudden we're in like a downturn on the economy, and then everything from then is down. If you train your model with just that first part, it's always going to be like, oh yeah, it's all going to go. We're going to the moon. And then when you're testing it with the negative stuff, it's just always going to get it wrong. Whereas if you feed it the entire data set, but not in like the entire, but you just take away 20%, but like a distributed 20%, then it knows not just happiness, but also sadness. And so it can predict a little bit better that way. So that's kind of the idea here, that we want to train it with the entire range of points, but we don't want to cheat and use points that we're testing with to train it with. And so we just randomly take out from the entire timeline 20% evenly distributed, okay? It's a much cleaner way of doing it, both for your training, but also for your testing to not be biased and to be more, ultimately we don't want our model to artificially look good, either because we're doing it intentionally or because we just don't know any better, because both of them will end up in a questionable output, ethically questionable output, whether your model is good or as good as you claim it to be. And reproducible research is a big issue, so I got papers on that stuff, so you don't want to go there. So if you follow my last video, I showed you how to do splicing, and I said in this video I will show you how to do that randomization split. So I'm about to show you that. Okay, so let's go ahead and split the data into training and testing sets randomly. And I'm going to first create the results where I'm going to store them. So I'm going to have my X train and X test. X train will contain the 80% that I want, and X test will contain the 20% that I want to test. And similarly, I'm going to go ahead and do that with the training for the Y and the Y test. So Y train is the output of the X test, and X train is the output of the Y train is the output of the X train, and Y test is the output of the Y test. X test. Excuse me. Y train is the output of the X train. Y test is the output of the X test. Okay, that is like a tongue twister. All right, but we got it. So that's also why you gotta be careful when you randomize it, because when you randomize it, you don't want to mess up the matching. You know, like you want to make sure that when you're testing it on your inputs are from like February 5th, then your Y should also be from February 5th. You don't want to like mix those up, right? So fortunately, this function handles all of this for you, so you don't need to know. You just need to, remember it basically. And it's just called train test split. Why is it underlined? I don't like why it's underlined. It bothers me. Is it not remembering that it's a function that exists? Oh, I gotta import scikit-learn probably. I haven't imported yet, actually. So from scikit-learn, import, or actually from scikit-learn's model selection, yep, import train test split. Okay, so what I'm doing is I need to import this awesome, cool function that was going to do all my splitting for me, that is made by the scikit-learn people. So it's called train test split, and it comes from the model selection part of the library. So I'm just importing one function, so that's why I wrote it like this. So now it's not underlined, so now it recognizes this function as real. It's like, yeah, it's a real function. Okay, so what I need to pass the function are going to be my x's and y's that I created up here, crypto x and crypto y. So make sure you don't screw up the order of these things. And then there's a couple of extra parameters that you want to put. The first one is going to be the test size. So I'm doing a 80-20 split, and by that I'm saying that if you think about your data, you want to train with a lot of data, because the more data you have to train, usually, I mean, there's a limit to these things, but like if you ideally want to have a lot of data so you can have a model that is like that knows everything. It's been through everything, like the ups and downs of crypto, so it knows. However, if you feed it all of the data, then you have nothing to test with. So most people will agree that a good split is to have 80% to train and then 20% to test. Some people will do like 90-10, but sometimes I think 10% is a little bit too little for testing purposes. And 70-30, I think it's a little bit too low and too much testing data. Unless you were doing something like train test validation, in which case I would do like 70, 20, and 10. 10 for validation, 20 for test, and 70 for train. But like I said, even though it looks like this, we're still doing it randomly. Okay, so that 20 is actually being yanked from all over the place. Okay, so I'm gonna go ahead and say 20%, 0.20. So you use decimals for this. The other thing I'm going to use, so here's the thing, when it comes to randomly picking things from here, I don't, like there's a small chance that like you could get really lucky in the way you take data. I mean, in theory, if this is truly random, I could just get so unlucky that like I literally picked the last 20%. Like it's just one of the possibilities, right? It's very unlikely from like a statistics point of view, but it's possible. Regardless, if you're trying to make your research reproducible, even randomly should be something that should be reproducible. So you just don't win the lottery that was like, you're like, oh man, when I did my model and I tested it like that one time, like it just nailed it. Like I got perfect everything. yeah, you just got lucky maybe. Because like when I ran it, I got really crappy results. And so how do you argue like that you're actually legit telling the truth or that you were not like just BSing it? And so you want to have randomness, but you want to have predictable randomness. So you can actually pass in like your seed value for the randomness into all these random functions in scikit-learn. And it's called the random state. And just pass in the number that you want to use for seeds. So I'm going to, do 42 for the memes, all right? Answer the universe, right? And so that's what I'm going to do. So now this is truly random, but this is always going to do the same random. So it's always going to split it the same way randomly. So whether I run it today or tomorrow, the data sets are going to be split exactly the same way. It's random. Like I don't know what's going to happen until I run it once time, but after that, it'll always be the exact same. If I want to try a different random to see if I'm not just really lucky, then I can change this or just remove it. But at least I know that that I can repeat the result and know that like this randomness is not one of the reasons why sometimes I'm doing good or sometimes bad. I have consistent results so I can focus on other parts of this, okay? So that's kind of the whole argument behind using this. But feel free to try out different numbers here and see how it affects the splitting of this. Okay, so now that I've split my data set, I am pretty much ready now to create the linear regression model and then train it. So let's go ahead and do that. I'm excited. We're almost there. How long have we been doing this for now? 1 hour. So we're 1 hour deep in this, and we're just almost ready to run the machine learning on this. Again, the data cleanup is worth it because this data that we're using now, we can use in the future for other things. So totally worth it, and a good practice of that as well. A lot of the times you watch videos online and they show you just how to use the scikit-learn machine learning model, and you're like, how do they get the data there? A lot of things that you have to do to get a data ready to go. The model part is just a tiny piece of the work. Like I said, with data analytics, a lot of the time, the work is really just preparing the data for a model to understand and interpret it. We haven't even got into things like normalization and standardization of the data sets. So yeah, data cleanup and preprocessing is a big deal. So, but anyways, let's keep going for now. So let's go ahead and create a linear regression object. So this is going to be where you're going to be using, you're going to decide what you want to use, which, like I said, we're doing linear regression, but you could also try to do another model, and we will eventually. Okay, so we're going to import the linear model, okay? And we're going to call that just regression, and there's a couple of them. Logistic regression we'll look at later on when we do classification. There's also polynomial stuff in here too. In fact, let's really briefly look at some of these. Logistic, linear, there's like a polynomial one somewhere here. I know too. Passive aggressive, that's cool. Base, yeah, there's a lot of things here. But anyways, the one we're gonna just do is a simple one. It's just the linear regression, okay? We could change some parameters in here. You can look at documentation for that, but now we're going to keep it default. We can go back and tweak that at some point if we feel like it, but I think this will be good for now. Okay, we made our model, or at least we picked the model that we want to use. Now comes time to actually train it. So we're going to call fit, and it's going to feed it the training and the training data, and it's going to hopefully train the model successfully. Okay. So this is the exciting part. So train the model using the training data set. So I'm going to call the fit function, and I'm going to pass in my training x and y. Train, and then my y train. Again, what I'm doing here ultimately is you can think of it like y equals mx plus b, right? That's your linear regression, right? So y equals mx plus b, this is your slope, and this is your bias, or also known as the y-intercept, right? So you have data, and what you're trying to do with this data is you're trying to create the best line that can fit this data so you can predict, right? And then you're going to compute the errors like this, figuring out how far away you are from the line. The way this line can be is this line could potentially be more steep. So a steeper line or a shallower line. You could also shift the line. So for example, even if we keep the same line that we have, it could start up here, or it could start down here. Right? So the shifting that we're doing, this is your bias. This is your y-intercept. That's that plus part here. Or it could be minus something, plus negative number, right? And then the steepness of the line, so whether the line is going like this, this, or this, that's your slope. So between those two, you're able to position the line where you best want it to be at. And so to do that, you're feeding it a bunch of pairs of data, you know, like 0.1, 0.2, 0.3, 0.4, and then you're also feeding it your input features. And using those, you start out by just picking something as a bias. Most of the times you start with a 1 or a 0, like that's what the algorithm picks. And using those, you basically do the algebra to try to compute what the best fitting slope is to reduce the error that you have. And after you do that a couple of times, you rinse and repeat until your error goes down and doesn't get any lower, or the change is very tiny, and then you call it a day. Now this is a one-dimensional scenario. Well, X and the Y scenario, right? Two-dimensional, I guess you call it. However, we have 3 features. So that is like, technically would be like a 4-dimensional hyperplane. So on 2 dimensions, we have a line. On 3 dimensions, we have a plane. On more than 3 dimensions, we call it a hyperplane. So in our case, which will be a pain for graphing actually, we could have something like x1, x2, and y. So x1 could be like the BTC opening, and this is like the BTC close price, which is just called price, remember? And then this is your Ethereum closing price, which is what you're trying to predict, right? So in this case, you know, this could be like a 3D graph, and now what you need to create is like a plane, which that's not easy to do, but like imagine there's a plane here, right? And so that would be for 3 dimensions. For 4 dimensions, I'm not going to try to graph that, because yeah, if you can't even graph it feasibly, it looks pretty. But yeah, so that's what we're trying to do, is we're trying to think of like predict the line that we're from our data. Okay, that's the math that's happening behind this. Okay, so we're feeding it our x and y values so that it can actually compute that. So that's what's happening there. Okay, so this is the training part. This is like literally the hardcore part. This is what would take hours if you were doing some fancy model, because this is working through this until it figures out. However, we're only working with under 1,700 data points, and it's pretty simple data. So and I have a pretty robust computer here, so it should be done pretty quickly. Let's just run and see how long it takes. It took about 1 or 2 seconds. I could time the code. I could write some time code. In Python, you can write the word time in front of it, like time, Python 3, name of your file.py. You can time it that way too. But yeah, okay. So we know that it finishes quick enough for this video example. That might be an issue when we're running like neural networks or something. We'll have to be careful of that. But okay. Now let's see if this actually trained and worked good, or like if it's a bad model. Like, I don't know, it's good or bad. So let's go ahead and test our model by making predictions with the model we just trained and comparing them with the test, with the expected results in the test data set, right? So what we want to do now is we want to take our model, like our nice little formula that's like y equals like 5x plus 5 or 5x plus 1, whatever the weights are. So we call these weights. If you look at a machine learning book, you got things like W1x plus W2x plus W3x plus B. So this is kind of what we have, because we have 3 features, right? So we have weights 1, 2, and 3, and then our bias. So these weights have been computed to be some number. So like, I don't know what these numbers are, but let's just make up a couple. I don't think they're all under 1, but for some reason I did that. and then y is like 5, okay? So these are the numbers that it's computed. So now what we got to do is we feed it in 1 point from our test data set, which is like some x values for this, compute that y, and then compare it with what we expect the y to be, which is correct, the correct one, and see that difference. So that's what we're going to do now, is we're just going to feed it all of our test examples and store those results so we can compare them in a minute here, okay? So I'm going to store them in a variable called yPredict. I'm really excited about this video. I like it. This is a very wholesome example. I'm going to feed it the test ones. I don't need to feed it the y test because I'm going to compare them in a minute here. All I want to do right now is just feed it our x's and get some y's. And now I want to compare these y's with my y test ones and see how good they did. So that takes us into our metrics section of the list of things we're doing. So if refresher, this has been an hour. Data, preprocessing, training, fit, predict, metrics time, and then graph and visualize. So time for some metrics. So from scikit-learn, we got all the metrics we need. We don't need to do the math by scratch to do things like mean square error and mean absolute value. They are all done for you. You just got to import them and use them, okay? So for example, we can print out coefficients just for fun. All right, but yeah, let's do things like mean absolute error. Let's also print out mean square error. And then from there, root mean square error, which is the same thing as the other one, but taking the square root of that. And then R2 score as well, which is the coefficient of determination. Okay, so let's go ahead and get all of these printed out. Okay, so for the mean absolute error, we can use the function mean absolute error. Hold on, metrics, plural, mean absolute error. And what we need to pass is what the model predicted and what we were supposed to get, so that we can compare those two and see if they're equal. It doesn't matter the order you pass them because of the way the math works for this. Here, I'll do a quick summary of that. If you recall, what you're doing is you're taking your predicted value and your test value. So let's just say the predicted one's like an uppercase y, and the test value is a lowercase one. And in the case of mean absolute error, you're taking the correct value minus the predicted value, and then taking the absolute value of that. That way, if you're trying to predict this point and you guess something up here, this is a positive difference. If on the other hand, you're trying to predict this point and you get down here, this is a negative difference. But they're both differences, right? If you just add all the differences together of all the points you're predicting and then take the average of that, these are going to cancel each other out. So to avoid that, before you add them together, you take the absolute value. So then if this is like +5 and this is -5, if you don't do absolute value, then this would literally be 0 and your model would be like, oh, I'm perfect. But it's not really. However, by doing absolute value, instead of getting 0, you're going to get 5 + 5, which is going to be 10, and then you do the average of that, which is divided by 2 because there's 2 points. Here you do average of 0 divided by 2, but that's still 0. Would you get 5? Now this 5 is more accurate than the 0 to actually portray what the real error is here, right? And so that's how mean absolute value works. For mean square error, what you're doing is, instead of another way that you can keep things positive, but not use absolute value, is to use powers, right? So you can just square this number. So you take this number and you square it. Again, if you have a -5, it just becomes 25. If you have a +5, it's just 25, so it's always positive. So then you do the average of that. So in this scenario, we would basically have -5 squared, and then 5 squared, which is going to be 25 plus 25 is going to be 50, and then take the average of that, which is going to be 25. And that's your mean square error. And your root mean square error, you take the square root of that, which is 5. So you actually would get the exact number as the mean absolute value error here. Let me just finish writing that. So you do the sum from I to n, I suppose, from 0 or from 1 to n, whatever this is. N is the total number of items you're doing the average of, and then you divide it by this n, and then that's your mean square error. If you want to do the root mean square error, which is just take the square root of that. And here it's the same thing. So the sum from I to n, 1 over n. You don't need to do any square root there. Okay, so that's your mean absolute value error, which is just called mean absolute error. And this is your mean squared error, right? Root mean square error, because you take the square root at the end. Again, root mean square error is more sensitive to outliers because it really punishes you for an outlier because it's a square part. If you look at my previous video on the data analytics times series, and you will see examples of me doing that root mean square error and showing you that it does affect the outliers, whereas it's more consistent with the mean absolute error. In fact, Wikipedia says I thought I found a nice little thing that explained it on Wikipedia. Root mean square error is the effect is proportional to the size of the square error. Thus, larger errors have disproportionately larger effects on root mean square error. There was a nice sentence that kind of summarized it. Just check out the Wikipedias for them. But like basically, what I'm saying is right. The mean absolute value error is a more consistent, so it gives an equal amount of weight to each error, whereas the root mean square error gives a higher emphasis to an outlier. So like one outlier will really punish you and give you a bigger error, versus like mean absolute error, one outlier is not going to break your grade per se of how good this thing did. Okay. Anyways, that's the mean absolute error. Let's get the mean square error in here. Same story, just call the metrics mean square error. And again, doesn't matter which one you pass it because you're just doing a subtraction and squaring that number. Just make sure you don't pass it like the x stuff. You want to pass it the y ones. Okay, so we're passing it those. And then for the root mean square error, we just gotta take our mean square error and take the square root of that. Right, so get this data and then take this number and take the square root of that. I do have to import a square root function, which I could do the one that suggested there from CMath, but I'm just going to do the one from NumPy, personal preference. NumPy, not num. Okay, it's just to call square root. Okay, the R2 score one. Let's oh yeah, it's just called R2 score. I'm trying to remember. This one I think it'll look better if we just print it out with this like that. Okay. And then so it's going to be metrics R2 score. Y test, Y predict. Okay, so that's all of them. Can I put to the next line without Python yelling at me? So that it just looks so long. What about here? I don't really have a spot to break this. Oh well. Okay, so let's run it. All right, so we got some nice numbers in here. Okay, so let's see what we got. We have some coefficients. You can look at those on your own. This is really what's going to tell me more quickly what's up with this. So we can see we have a mean absolute error of 15.89. We have a root mean square error of 29. So the fact that the root mean square error is bigger than the absolute error is typically standard. Probably outliers are raising this a little bit, and there's definitely some outliers. Our R2 score is really high, actually. It's not bad per se, but impressive actually. Something's probably a little bit. It's probably a little bit of overfitting going on with the default parameters. But yeah. So to understand what this means is this is in dollars per se. Okay, and so the reason why this is not this to be taken with a grain of salt is because the price differences, as the value of crypto of like Ethereum and Bitcoin went up into thousands of dollars versus being like $15 for Ethereum or Bitcoin, you know, an error difference of $10 or $15 is pretty small. But in the previous ones, when it's looking at the error for the ones that are like $15, a difference of $15 is like completely twice the amount of the value, right? So you got to take that with a grain of salt, that the scale is, because the scale grows in the terms of like how much each crypto is worth, the error may look mischievously low when it's probably a little bit higher than that, okay? However, it's not bad. Basically, it's saying that given the Bitcoin's opening price and closing price for the day, and given the starting Ethereum price, we can guess what the Ethereum closing price is within a error margin of about, conservatively, of about $30. So we're off by $30, conservatively. Ambitiously, I'm going to say we're off only by about $20, okay? So I'm basically taking this number and kind of the in between, I'm going to go with 20. Conservatively, I'm just going to go with 30 because it's bigger than both of these. So that's what I'm saying. You're thinking, wow, okay, if Ethereum's like $3,000, we're only off by like $15. That's a pretty accurate system. And I'll say, yeah, sure, as long as we're looking at those numbers. But if we're guessing the numbers when Ethereum was like $50, then that's a big room of error per se. It's like 50% room of error, okay? So there's probably some normalization that we'd have to do with the data set to improve our model. But yeah, it's not bad. So let's test it out with some actual data, okay? So like I mean, we're going to graph it, but I just want to double check. So let's, for example, let's see. Let's look at the last day of data that we have. Okay, so we know that for the last data point, we can see here that the Ethereum, the Bitcoin's last point for the, so I'm trying to remember, this is price, right? Hold on, head Bitcoin. Yeah, so we got price and then opening. So the opening price of Bitcoin on the last day of the data set was $49,532, okay? So let's take this point for opening, this point for closing, and then for Ethereum's opening of $3,300 and 22 plus 0.6. Let's take those and see how accurately we can predict this number right here, okay? So in short, oh, here we can see some of these numbers here actually. The first two at least. We want to feed this in and see if we can get the last value, okay? So in short, for a little sample test, we know that the correct value that we want to hope to get is going to be, oh, that's not Right. There we go. Darn it. Okay, so the correct value that we want to get from this is this number here. So this is the correct closing price. Closing price on 8/27 or 21. Ignore the random C++ code from a rogue tab. Go away, please. There we go. Okay. So this is closing price, and then it's on 24. Okay, so on 8/24, the Ethereum closing price was this. The opening Ethereum price was this. And then for Bitcoin's open and close, those we could see here, I think, are these two. So this is the close and the open, which to confirm does indeed match what I see there. Okay. So that's actually the close, and then this is the open. Okay, so the Bitcoin opening was this, the Bitcoin close was this, the opening ETH was this, and this is the closing price. So let's see if our model can predict that. Okay, so I'm going to go ahead and call the predict one. So I'm going to call print because I want to print out the results of this. And then I'm going to refer to my model, which is called regression, and I'm going to call the predict function again. And this time I'm going to manually feed it 3 values, but to be able to feed it, you can't just feed it a list. You have to, it expects an NP array. So just call the NP array function like this, and then feed it an array with the 3 values. Okay, so the order of them is going to be opening, closing, and opening of Ethereum. So opening, closing, and opening of Ethereum. Now this number, the last number, this could be in the test data set, it could be in the train data set. I don't know. So we'll see. Oh, because we don't have NumPy arrays there, it's saying it, so let me just import them. From NumPy, import array as NP array. Oh, also the fact that I did the NP there, but yeah. Okay. I guess I'm just used to doing that. Okay. Yeah, so this right here should hopefully be close to this number, okay? In fact, once we compute, let's actually, instead of printing it out first, let's just store it somewhere. So we'll call it answer. And then I'm going to print out the answer, but I'm also going to print out the correct number minus what the answer is. And then maybe the absolute value of that, so we can see how off we are. Okay, ignore the warning. It's probably because of the NP array. So the model predicts that the closing price of Ethereum that day should be $3,335.50. That's what it predicts. The correct answer is that it closed at $3,329.47. We are only off by $6.03. That's not bad. We're only off by $6. I would consider this a success, okay? Let's try, I suppose. I don't know where I can find it off the bat. Let's try data from like today or something. Ethereum open price. What is it? What's that one website? Okay, Ethereum price. I'm just Googling Ethereum price. Coinbase. I think that's the one that. Oh, no, it's no Coinbase. Okay, fair enough. One day. All right, this might work. Okay, so Okay, I don't know if this is these numbers are going to be very accurate per se, but it's going from like 5 a.m. to 5 a.m. because it is 5 a.m. right now, so that's very cool. All right, so it appears that the opening price for Ethereum was 27.2418. 27.2418. That is ETH open price. ETH close price was what it currently is right now, as of the time I'm recording this video. Hold 35. So, oof, went down today a little bit, but okay, not to worry. All right, let's go ahead and very quickly before the changes. Crap, go to Bitcoin's price from the same website, Coinbase. I guess Coinbase. This video is not sponsored by Coinbase, but if you're, feel free to donate. All right, let me actually refresh. So they're like the exact amount of time. Okay, so let's retake these numbers again. Whoa. Hold on. One day. Here we go. Okay. So actually, now we're looking at different numbers because I wanted to refresh them at the same time, so we got a good measurement. So it's 27.2379. And then 26.30.48. 26.30.48. A little better. Okay. And then the matching Bitcoins ones for this are 39.891. 891.25. And then the closing price was $38,240. About 97. Okay. Well, that took a while. Okay, so let's go ahead and for posterity, so this is from 2/20/2022, approximately 5:25 a.m. Pacific Standard Time. Rise and shine early, I guess. Okay, so we're gonna take those numbers and we're gonna feed them in. So this is our BTC opening price, right? So we're gonna put in. I'm actually excited now to see what happens here. And then the opening price for this. And then hopefully we get this, but I'm gonna put that there so we can see. All right, so moment of truth. What will happen? All right, we fed it in. It predicted that the closing price of Ethereum, those numbers don't look right. It predicted that the closing price of, oh, wow. Whoa, ooh, okay. They are right. So it predicted the closing price of Ethereum was going to be $2,644 with 2 cents. That's the predicted one. In fact, here, let me label it for you. Oh, crap. Hold on. Not showing you what's happening. I apologize for that. Let me show you, backtrack a little bit. What I did was I just literally copied and pasted the opening, the closing, the opening, and the closing. And then of today's date, which is 2/20/2022. This is where I'm getting it from. You can see this is the number that I got from about here. I just basically put my cursor as close as I could there, and then just looked at the price here and put it as close there for that one, and then for Bitcoin, which is this one. Okay, so this is the numbers that I got live. Opening price, closing price, Bitcoin opening, Bitcoin closing. So this is, I'm feeding in Bitcoin opening, Bitcoin closing, Ethereum opening. I run it through my predictor, my model. The answer I get back from this, so this is what the model predicts. And this is what the error is. The model predicts that the closing price of Ethereum that day is $2,644.02. The real price, the real closing price that I looked at was $2,630.48. We are off by $13.54. So within something that is worth close to $3,000, we're only off by $13. That's not bad. But then again, this whole logic is that we know that the Bitcoin price and the Ethereum price are kind of tethered together. So when one goes up, the other one goes up. Not always, actually, but that is the trend. And our model picked up on that. Without us telling our model that, it picked up on that. And that's why it's succeeding in knowing that that day, basically, Bitcoin went down like $1,000, basically. And Ethereum went down about $100. And that's what our model predicted. In fact, our model was a little bit optimist. It actually predicted $13 higher than what the real price was. So we have a little bit of an optimist model in this exact day. I consider this a success. But like I said, we're going to try this with other models, other like machine learning models, and see if we can improve these results. It's very cool. Like, see, this is when you know you're into data analytics. Like, you see this stuff and it gets you excited. So it gets me excited. All right. So hopefully you saw a nice example. But now let's look at some graphs and see if we can. It's not going to look pretty because it's a 4-dimensional thing. But let's try at least and graph something. Let's see what comes out. Okay. So let's just kind of work our way. This is like icing on the cake now. All right. Let's try to plot the output and kind of visually see how our model performs, okay? So for that, we're going to be using matplotlib, the pyplot, okay? And we're going to make a figure because it's going to be 3D, basically. And then we got to set it to make it a 3D figure, so we're going to use axfig add subplot, make it projection 3D. Yep. Okay. So the best thing to do is to make a scatter plot, because otherwise it'll look nasty. So it's just a bunch of dots. So let's plot the predicted ones versus the expected ones and compare them and see how close they are. Okay. So I'm going to put scatter and I'm going to pass in here the columns that I want to print. So let's print out the opening price as one of the axes. And then let's print out the closing price as the second axis. And then let's print out the correct values. And let's color these black. Okay. Let's just see what that looks like first. So let's put some labels in this. So let's do X, Y, and Z, and then this is Ethereum close. Okay. I don't remember if I gotta put the function xtick, so I'm just gonna put it here anyways. I don't know if you need this. Just, let it be. And then I always forget this, but I call show, otherwise we don't get to see anything. All right, so let's just see that, see if it works. Okay, so ignore that then. Let's not put that in. Maybe it'll work now. Okay, nice. This is better than what I expected, to be honest. I don't know why some of those are grayer than the other ones though. But okay, very cool. So we're not even graphing all three features. We're not graphing the opening price of Ethereum. We're just graphing the opening price of Bitcoin and the closing price and how that relates to the Ethereum one. So you can definitely see that there's a trend, right? You can see that what we want is a line in there. Well, not a line, I guess, but a hyperplane that kind of chops this in there. So we kind of want to put something there, like there. This will work pretty well with support vector machines, I have a feeling. But yeah, so okay. So now that we saw what the expected one is, let's see what the predicted ones are and how close they are. So for this, instead of passing it by test, we pass in what we predicted from our test data set. And let's make those blue. And as you can see, it's really hard to see, actually. As you can see, it's hard. But the black dots and the blue dots are like touching each other, essentially. They're really close, and that's good because that means that we're accurate. Look at that. Look how cool that is. I love how you can manipulate this, but like, you can kind of see that's what we want. We want to do something this way. I mean, like, this is just, oh God, this looks nice. This came out better than better than I expected. But yeah, so like if we were just looking at the BTC and the ETH close, we can see that there's definitely a line on this dimension. On this dimension, which is the BTC open and the ETH close, we can see that there's another line as well. And from this dimension, with BTC open and BTC close, those are kind of related too. So yeah, but if can we zoom in more? No, it won't let me zoom in more. So sad. At least I don't remember how to zoom in more. Oh wait, there we go. So you hold. So you can see, for example, like these two dots right here, or these two. The bottom one, I know it's really tiny for you, but like the bottom one there, this one, blue one, is what we predicted, and this is what the expected value is. So you can see they're really close. And the same story for most of them. In fact, there's a lot of overlap for the ones at the bottom. Like, it's really good with those bottom ones. The worst one that I see so far is like this one. This is the predicted and this is the expected. Those are kind of far. But yeah, this kind of shows you that our model is doing pretty good, pretty darn good. They're really close. Some of them are overlapping even. Like these two are overlapping. That means that like we don't. I mean, it's probably not exact, but like we're probably out by like pennies. Okay. Great success. Great success. In fact, great success in the graph itself. Matplotlib can get finicky, so I'm very happy that it actually didn't explode on us here. If I try to do a line, I don't think this will look pretty. Let's try to do a line and see what happens. So instead of doing that, lines only really work when you're dealing with 2 dimensions. When you're dealing with multi-dimensions, the lines are going to look really weird. But I'll show you. So we've got the opening, the closing, prediction, color, so green. Let's do some line width of like 2. So if I graph that, let's see what happens. Yeah, that does not look good at all. I probably could improve it, but the reason why is because it's trying to connect all the dots together, and so it's like going back and forth. It's like going like this. So it's not really accurate. It looks cool, but I think just the dots themselves represent better than this. But hey man, this could be our crypto. If we make a crypto, let's make this be our logo. I don't know. Let's call our crypto the Analyticum. The DA Analyticum or something. Let's make some NFTs. Make that an NFT actually. Somebody make that an NFT of that picture. I'm not buying it though. Okay? So yeah, don't like that one. But I do like the dots. The dots are better. They're nicer to visualize. They actually tell you a better story. If you're showing this to someone that has no idea what you just did, I think that this will kind of show it better to them. Maybe instead of using circles for one of them, you can use like crosses and then put like shapes, because it's easier to differentiate. Plus, you don't know if they're colorblind or have issues with colors, so you want to make things accessible. So, go ahead and do like shapes. But yeah. Okay, maybe one more thing I'll do, just plot-wise. Well, no, I mean, what I could do is I could try to make a line that's like a 2D one. But you can already see what 2D looks like here. You just rotate it to see. Like if I wanted to see 2D, this is what 2D looks like. So it would just look like this. But still, you can see how close they are. In fact, if there's a specific dimension you're looking at, like this versus this, that you see is more often the other one, then that's a sign that that's the one that you got to look at more carefully. Like for example, this looks a little bit better. They look about the same, but yeah. In fact, actually, you know what? Let's just see really fast what it looks like. If instead of doing maybe the open and price. Let's change open here to the Ethereum opening. Let's see what that one looks like. See that relation looks like. So now we're only, again, we got 3 features, but we only graphed 2 of them. Ooh, interesting. So you can see the relation between the opening and the close. And this is one that we already seen. So you can see that as it figures, like the opening and closing price are related. Those are really accurate. So it's definitely, our model is definitely doing pretty decently. So anyways, enough looking at circles. I think we proved our point that something as simple as linear regression can work whenever the data is actually expected to. I mean, again, this whole thing started with the premise of like, I knew that there was a relationship between Bitcoin and Ethereum price, right? But I welcome you to try this out with other cryptos, which there should be also, especially with the altcoins. Those altcoins are really tethered to Bitcoin, with the exception of when there's like special events, like Dogecoin. Like when Dogecoin mooned after like Musk's tweets, right? Your model probably gets all screwy with that. So that would be interesting to look at, actually. Yeah, that actually would be cool. So, but yeah, let's really quickly summarize, just quick summary, and then I think we can call it a day on this. So what we did is we downloaded our data from Kaggle. Over here, we got our data from Kaggle. I don't know how you pronounce it. We went ahead and opened it. We have different rows count because of the Bitcoin being longer than the Ethereum one. So we went ahead and we looked for the only from 2017 and on dates. So we went ahead and dropped the rows that were before 2017 on both tables. First, we started by doing everything with Bitcoin, and then we applied it to Ethereum because we got it working for Bitcoin first, and we tested it and we moved it over. We also removed this SNO column that was really useless and we didn't need it. After we did that and we prepared the data, we make sure that they had the same number of rows, which is 1,697, I think, recall. And then from there, we went ahead and we Lego them together. We combined them together, put them side by side. By doing that, though, we had issues with the names because the column names were the same. So we just renamed the column names so that they're easy to organize. From there, we were finished with the cleanup stage of the data set. So now we went ahead and created our training and test by creating an X and Y's. So we only took 3 features, which are the Bitcoin's opening price, Bitcoin's closing price, and the Ethereum's opening price. Those were our input features. And then our output is the Ethereum closing price. That's what we're trying to predict based on the input. So we went ahead and we copied those columns over. Then we go ahead and split it 80-20 using the train test split function in scikit-learn. That pretty much does it all for us. We do have a random state 40 here. We can change this, and we can see, let's change that actually, and then see how that changes our mean square error. It'll slightly change it actually. I just gotta figure out where I'm printing out this whole thing. Oh, here we go. We can still see it. So you can see our mean square error in this case is 45.01. Okay. Now, if we undo that change, 45.01. Ooh, wow, that's a big change. We go from like 29 to 45. So you can see that the way that the data set gets split can really affect that. So, okay. We'll have to look at that. I guess like we did get a little lucky there, but still, it's still within a nice range. So you can see that by tweaking that around, we want to have a predictable randomness, so that we can verify our results with others, and we can tweak this without having to have luck play a role in it. You know, we remove the randomness, but we still have it. It's just predictable randomness, so that we can experiment without having to worry about randomness affecting whether our result is better or not after tweaking it, just because the randomness got lucky us this time. So anyways, that's what we did. From there, we created our linear regression model. We trained our model by feeding it a training data set, which is 80%. And then we predict with the 20% that we have for testing. We store those predictions in here, and then we compare them with what we expected, and then measure the metrics of mean square error, mean absolute error, R2 coefficients, and so on. And we get some numbers out of that. They're not perfect, but they're not bad. I'm pretty happy with how our model predicted things would run, actually. How did it do with the modern day data, by the way? If we switch it to 40, I forgot to see that. The error is only off by $10, actually. So even though our mean square error is higher, with today's prediction of data that I loaded it's actually better. So interesting. Interesting how that actually turns out. Yeah, it's slightly better. So our model went down from being off by $13 to being off by $10 whenever the randomness changes. Again, you take that with those numbers with a grain of salt because of the randomness, okay? Ideally, you want to run this a lot of times and sort of average that out before you can claim your model is really good or not good, I guess. Well, you know when it's not good regardless. Anyways, that's the metric part, and then of course I graphed it so that you could see that things look pretty. That's just eye candy at the end of the day, but it's like your trophy, you know, your picture is your trophy. All right, so that is the end of the video. I thank you all for watching, and I hope that you learn and that you now feel comfortable going out there with scikit-learn and applying it to your own projects, whether they be crypto or not. So thank you all for watching, and I'll see you around in the next video where we will try out some other machine learning models. All right? Thanks for watching. Take care and hold.